It by default does not turn the microphone on. So, electric potential, energy, electric potential. So there's other sources of electric potential. The parallel plate capacitor, right? You had an equation for that, but I did not include the potential, but I'm just kind of as a reminder, right? When you're studying, right? You have the parallel plate capacitor, and one plate has a positive Q and the other plate has negative Q, right? So if you are tracking the potential, it's going to go from positive to negative as you go from one side of the capacitor to the other. So don't worry. I guess I'm telling you not to worry. I didn't put potential due to capacitor on the final, okay? It's going to be strictly point charge. It had some function of x, right? It was like v of x equals, something. So, just kind of rounding out everything that we talked about. So we're going to focus for the final, focus on the potential created by point charges. And the potential difference. So we talk about delta V a lot, right? Potential difference is the difference in potential at different points in space. The potential difference. So let's say that we have a point charge here and a point charge here. And this is point A and this is point B. Okay, the potential difference, VA minus VB, we would calculate by first finding the potential due to each point charge, right? So we're going to have potential at point A due to the positive charge, potential at point B due to the positive charge, okay? And then we will have, that's A due to the negative charge. There we go. I was like, that doesn't make sense. So how would we calculate that? You'd use the potential energy function for a point charge, KQ over R. These are going to be your different R's. I'll call this R plus and R minus, right? So you're going to add up those V's. You might recall this from the exam now that we're looking at it. And that's going to be the full potential at point A, right? There's two sources of potential at point A. So it's 2 point charges right there. So that's going to be your potential at point A. But we want to know the difference between the potential of point A and point B. And the reason for that is because the energy is UQ delta V, right? So delta V, if we know delta V, we know how much energy it would take to move a charge from A to B. So I'm just telling you the motivation of why we need to do this. We're not just like computing random equations, right? So then we're going to find VB. It's going to have 2 contributions, right? The only difference is that B is at a different location. So B is at a different location, so we need to get our R minus and our R plus, right? So you're going to have different values there. And then VA minus VB is exactly what you think it is. You're going to take those 2 values and subtract them. And that's going to be the potential difference. So, the arrangement won't be so abstract like this. The arrangement that I provide will be like, probably squares on the corners of a rectangle or some well-known geometry, not like out in outer space floating around, right? So computing the potential difference. So look for problems that have you do that in relation to point charges. So this, the other idea here is that electric potential is not a vector, right? That's why it's mathematically easier. We don't have to worry about directions, x direction, y direction, z direction. All that matters is the physical distance that the charge is away from the point of interest. And then Q obviously would be positive or negative depending on what the charge is. So even though I have a plus sign here and a plus sign here, Q is negative, right? So there's a negative sign inside there. So when I'm plugging in my calculator, right, I'm putting in negative value. So we kind of started talking about capacitors before we talked about this. I'm not going exactly in order of the way we were taught, but it's just in the order that the questions were laid out. So let's talk about capacitors. So the capacitor is like our first application. So parallel plate capacitors. Is we're applying everything we've learned to that object, right? And what is a capacitor? It's simply a positively charged conductor next to a negatively charged conductor, right? And separating them is a non-conducting material like air. And so we care about the distance between them and the charges on the plates and the potential difference, right? The delta V between them. And typically at this point we drop the delta. So this is where why potential students get really confused with potential is by convention we just drop the delta because I don't know, maybe we're tired of drawing triangles, I don't know, right? It's just by convention you drop the delta and the V implies that you are looking at a potential difference between two charges, right? Because the way you create a potential is by separating charge. And a capacitor is doing exactly that. So the capacitance of this arrangement is a ratio of the charge on one of the plates divided by that potential difference that's created. So that's the fundamental capacitance relationship. And then from that, you have a whole bunch of other relationships. So when you're looking at capacitors, you want to be really focusing on the relationships between the parameters, what parameters stay constant, what parameters are changing. So we have C equals QV. For a parallel plate capacitor, we can also express the capacitance as epsilon naught area of plates divided by distance between the plates. And so obviously, since C is on the left side of both of those equations, you could set those equal to each other if you needed to, right? To solve for whatever it is you've been tasked to solve. So we can now use the parallel plate capacitor to define electric field. Electric field is a change, I'll use the delta V, a change in potential over a distance. And you can know that from the units, right? The units of electric field are either voltage over meter, or a Newton over Coulomb, right? And that one comes from F over Q, right? So those are the two units that you can use to describe electric field. One, the newtons per coulomb, is more about when you're talking about forces, and then the other, the volts per meter, is when you're talking about electric fields and potential differences. So E equals delta V over D is the equation for the electric field inside a parallel plate capacitor. And so by looking at that, you can see that it's constant, right? It's a constant. It's a constant value. It depends on what delta V is and what D is, right? And those are fixed numbers. I mean, you can change you could change D, right? If D got changed, then E would change. So that's one relationship, right? E equals delta V over D. So if D changes, what could happen? If D changes, goes down, then E could go up, right? So another way to express the electric field between the plates of a parallel plate capacitor is by the charge density, which is charge per surface area, divided by epsilon naught, which is the constant, 8.85 times 10 to the minus 12. So that is the electric field value And you can see it depends on charge and area. So work on combining all of these together, understanding what happens to one parameter when you change the other. So, and there's I have some typical relationships, written there. So we're kind of like looking at the capacitor, right, in detail. We're studying it. It's our, the parallel plate capacitor. Let's zoom out a little bit. If we zoom out and look at capacitors, multiple capacitors in a network. And this is called capacitors in combination. So we're like kind of creeping into circuit territory, right? We're kind of slowly getting into circuits. And so for capacitors in combination, putting them in a network, oh, that's not how we draw a capacitor. That's a capacitor. Okay, so we have, let's say, 2 here. Okay, here's a network of capacitors. So we need to recognize series, the difference between series and parallel arrangements. When something, whether it's a capacitor or a resistor, is linked up in series with another object, that means that there are no junctions in between the two. If there are no junctions in between, then it's in series. If there's a junction, it's in parallel. So the rules for adding capacitors in series is you add them in inverse, and then you inverse the result. Right? You add the inverses, and then you do one more step, you inverse the result. For capacitors in parallel, you simply add together. So there will be a problem just like this, where all you're asked to do is find the equivalent capacitance, okay? And there might be one more step where you use the fundamental equation of capacitance to find either Q or V. Yes?
How many questions?
24.
24.
Yes.
So, when you're talking about capacitors, what resistance, is it like the inverse?
Exactly. Yes, resistance, the rules are reversed. They're flipped. Yep. So, before we get to resistance, it's on the way. We need to define current, right? Which is the flow of charges. So we are getting into current, resistance, and voltage and how they're all related. So current is the flow of positive charges. And so the magnitude of the current is how much charge flows through some given time, flows through some surface area, okay, some defined area. For example, if we have a wire and we are going to, have our little microscope and we're going to examine and we're going to count how many charges are flowing through that circular cross section, right? We're going to count how many charges. We're going to get a stopwatch to see how long it took for that many charges to pass through, and that is what the current value is. So it's a rate of change of current. And how does that relate? So this is our current. How does that relate to our potential difference? So there's our current. So, right, if we have a bunch of charges, positive charges moving over here, then they're leaving behind a buildup of negative charges, right? Essentially giving us a separation of charge, which produces a voltage. So the voltage across the wire And then the current moving to the right of the wire. Well, Ohm's law tells us the proportionality of that. Delta V equals I times R, right? So R is kind of like the proportionality constant that tells you how much current you get for how much voltage you apply, right? Because what we do in the lab is we create a potential difference to motivate the charges to move, right? Because potential is related to potential energy. So if we create a potential difference, that means we're giving the particles energy to move, and we're motivating them to move. And however many we get to move depends on the resistance of the thing, right? So the bigger the R, the less current you get to move, right? The bigger the resistor, the less current moves through a given potential difference. And vice versa. The lower the R, the more current you get to move through a given potential difference. Right? Because this potential difference is usually fixed by the battery or the power supply, or whatever, not a capacitor, because the potential does change, right, as the capacitor loses its charge, right, in a circuit. So fixed by the battery or power supply, right? So delta V is constant, fixed. So if you are putting in different materials of different resistances, they're only going to allow so much current to pass through depending on how big the R is. So, so the resistance is a parameter that depends on the shape of the object and then what the object is made of. So rho is what we use to define the resistivity of the material that is that the thing that the resistor is made out of, right? And then we are gonna put some geometrical factors in there like length and cross-sectional area. Right, so this isn't just any area, this is the cross-sectional area, which for a cylindrical wire would be pi r squared. Length is obviously the length of the wire. So this is how the resistance is, is found, right, for any particular object. Is you take the resistivity, which is kind of like the tabular value of how resistive that material is. Like, gold has a very low resistance, copper has a very low resistance, air has a very high resistance. So the relationship between resistance and resistivity, what I would, usually the question that is asked is a proportional reasoning question, so be prepared for that. Something like what was already previously tested on. So basically, like, what happens if the area is decreased by a factor of 4? How does that affect the resistance? Okay? So, so now that we're getting into resistance, let's talk about resistors in combination. Well, proportional reasoning is, I guess, technically conceptual. Technically, this is a conceptual. I mean, there's a little bit of calculation, right? But it's not like a serious calculation. Like, what happens if you increase this parameter? What happens to one parameter if you increase the other, right? There's a little bit of calculation involved, but, it's mainly a conceptual.
Like a roll, and like if you increase the length of the roll, then how much is the resistance?
Exactly. Yep, so that's a conceptual question for the most part. So resistors in combination, so you're going to follow the rules. So you'll get a network of resistors, okay? And you'll need to identify if they're in series or parallel And then the rules for adding these are going to be opposite to capacitors. So for resistors and series, you'll straight up add them, while resistors in parallel, you add their inverse and then inverse the result. So identifying, let's kind of do this one real quick. What you want to do is you want to start on the right, and this is good for capacitors as well. So what you want to do is start on the right side, and you want to pick two that are closest together, and then you want to look at them and you want to see, are there any junctions between those two? If there's no junctions, then you know that they are in series. And then those two will be replaced by one resistor. And you can just pick either location to replace it. So let's draw the equivalent circuit with those two replaced. Right? I'll put them both right there. So this is going to be R1 plus R2 right there. Right? So I'm going to keep progressively combining them. So now it's pretty clear that these two are in parallel, right? Because there is a junction between them. So now I'm going to add those together, but I have to add them in inverse, right? And then I'm going to pick a location to replace that. So what I can do is I can go ahead and draw my new, right? This guy is going to be well, let's figure out what this guy is going to be. So we're going to do 1 over R3 plus 1 over R1 plus R2. And then that whole thing is to the negative 1. So that's what his value is. Right? I'm doing it algebraically, but you'll have numbers to work with. So you can plug in your numbers so you're not dealing with like strings of letters and subscripts. And then now we're going to link up these two, and we can see that they're separated by a corner, and a corner is not a junction, right? It's just a corner. So now we can add these two in series. What was this? This was R4. So then the total equivalent resistance across these 2 points would be R4 plus that thing. Okay, and you plug in your values. So practice condensing down large-ish, not much larger than what I have right here, okay? 4 or 5 resistors or capacitors, right? Both are gonna be on the exam, okay? You'll have a little network of resistors and a little network of capacitors. So that's, I guess technically that's like a conceptual, I don't know, it's kind of like halfway. It's a calculation conceptual question. Okay, it's just one of them. So, RC circuits. Next, one question, one calculation. And it's going to be just like what you've already seen. So, right, a capacitor, when it's linked up with a resistor, and if there is also a battery involved, then you know that you are dealing with a charging capacitor circuit. How do you know it's charging? Because that's what the battery does, right? The battery is charging up the capacitor. It's putting all the Q on the plates, right? It's putting Q on the plates. So you have your charging equations. For voltage, for charge, and then you can use your fundamental capacitance relationship to convert those values to anything else, right? C equals Q over V. You could also use V equals IR if you were asked for the current through the resistor, right? You would you would use your V equation and then divide by R to get I. Okay? So Q would help you find either the capacitance or the voltage as a function of time, and then the voltage equation would help you find the current through the resistor. I think in the formula sheet I gave you all the formulae, right? I didn't just give you Q and V. So you'll have all those still. For discharging circuit, you don't have a battery. So that's how you know you're discharging, okay? You don't have a battery. C is acting like the battery in a discharge circuit. C acts as the battery, right? It's discharging. It's sending charge off of its plate, and if you have moving charge, you have current flow, right? So C acts as the battery, providing the current. And then the discharging equations, you know, for example, this would be Q naught. T over RC. So a very straightforward application of RC circuits. There might be one extra step where you need to convert to some additional unit, right? There's one extra step, but nothing crazy. So Kirchhoff's laws, it's not on here. I don't think I directly test Kirchhoff's laws. So you're welcome. Yes.
No RC circuit problems with switches.
Well, okay, so yes, but that won't change anything. So basically, when you have a switch, all that is doing is controlling when you start the charging process or when you start the discharging process. So the switch there does not affect what you do in any way. So don't worry about switches. I remember, it's so funny because I remember like when I first learned this, the switch bothered me too. I was like, what is a switch? I don't get it. I don't understand it. You know, and then it doesn't really affect anything. All it does is it's just showing you, you know, in reality what's going on when as soon as you close the switch, then you get the current to flow and you can start tracking the time. But it's funny, I was like, these switches. So let me just look at the final real quick. I want to make sure that Kirchhoff's, because I didn't realize until right now that Kirchhoff's was not on there. I think I judiciously, yeah. No Kirchhoff's. Only, yeah. So don't worry about needing Kirchhoff's loop rule or junction rule. I mean, you don't need to use it. It's not necessary.
Is that on the formula sheet you gave us?
Is that on the formula sheet?
Yeah, the Kirchhoff's.
Yeah, it should be on the formula sheet from exam 2, or exam 3. Yeah, it's just sum of all voltages equals 0 and IN equals I out. Those are the only, that's what it is. IN equals I out. I'll write what it is just for. And then I into a junction equals I out of a junction. Those are Kirchhoff's rules applied to circuits. So yeah, you won't need it for the exam. So so now we're getting into magnetic field territory. Oh, we're gonna hurry. We gotta hurry. Let's do some right hand rules. So the first thing we talked about was how currents create magnetic fields. And then we talked about forces. So let's first talk about how magnetic fields are made. They're made by current. So let's say we have a current coming out of the page at us, right? The dot is a vector coming out of the page. So how do we know what kind of magnetic field is made? You put your thumb in the direction of the current using your right hand, and then your fingers are going to trace the magnetic field lines. So you can see they follow, they go all around my thumb in a circle. And that is a counterclockwise circle. So many different ways you can draw this. Let's draw from another perspective. So this section is all about 3D perspective. So let's say I is going this way. Okay, there's our little dot. So now how would we draw that, right? So I is in the plane of the paper. My fingers are on the top of I, are going to go into the page. And my fingers below I are going to come out of the page. Into the page is X's. Out of the page is dots. In and out. So above the wire you have out of the page, below the wire you have, above the wire you have into the page, below the wire you have out of the page. Loops of wire. Okay, you take that current carrying wire and you form it into a circle. So let's say that the current is now flowing in a counterclockwise fashion. So your thumb is the current direction and your thumb is going to trace the circle, right? Imagine it going around like that, right? It's tracing a circle. And then let's put my thumb where the curvy arrow is for I, right? It's right up there. Above or outside of the ring, you can see that my fingers are going into the page. But when my fingers are below the current, they're coming out of the page. So into the page at the top, out of the page at the bottom. And it kind of matches with the straight section. Right? Because this right here is technically a little straight section, isn't it? So it's going to follow exactly this stuff up here. You're going to have X's out of the page, dots in. X's into the page and dots out. I cannot say it right. I don't know why. You see that? Because one little section of the ring is straight, approximately. So you're just taking that guy and moving him down there, and then swinging him all around. So X's everywhere outside, dots everywhere inside. Okay. So there'll be a conceptual and a calculation for magnetic fields and for magnetic fields, and it might get tied into forces, right? These can kind of get a little combined together. So let's talk about the forces. So if you have a magnetic field pointing this way and a charge moving with velocity v that way, let's say it's a positive charge, then the force direction is going to be, using the right hand rule, fingers in the direction of V, sweep it into V. My thumb is pointing down. So V is going into the page. V is to the right. So V cross V, pointing straight down. So the force that the particle feels due to that magnetic field is going to point straight down. Now, if this was an electron moving in the very same direction, with the same magnetic field, you're going to flip your result, right? V and V, flip your answer. The force would be pointing up. So converse, you could also use your left hand if you wanted for negative charges, and you get it right away. Right away. Yeah, V is in the page. Yes, V is in the page. So there's another right hand roll, the 3-finger. If you like that, that's fine. V, you just want to make sure it really doesn't matter which fingers you use for which, as long as they go in the following order: V, B, F, V, B, F, V. You're right. So you can start V with your pointer, B with your middle, F with your thumb. It has to go in a certain order.
You said V, F?
Yeah, so let's stick with the textbook. I think the way the textbook does it is V is pointer, F is middle for F, and then thumb is, no,
V is
V is thumb. Yeah, that's right. V is, I was like, that didn't work out. F is the middle, yeah. V is thumb, B is pointer, F is the middle finger. So now let's do the positive charge. We have V is my thumb, B is B field pointing that way, and then you can see the middle finger. There we go. B is pointing into the page. That's my thumb. B is pointing to the left. Middle finger pointing down.
What about the wrapping that you do? So you wrap V to V.
Yes, so the way that I do it is, so basically this is a cross product of two vectors, and a cross product creates a third vector that is parallel, or that is perpendicular to the plane created by V and B. So when I do my sweeping motion, sweeping V to V, what I'm doing is I'm like laying out an XY plane, and I'm making my thumb perpendicular to that plane.
So sweep V to V.
And you always sweep V to V. You can't, if you do the opposite way, then you're putting a minus sign in there. So you always want to sweep V to V. So now where things get tricky is where we combine these two concepts, right? So now what if instead of me drawing a B field vector, I draw a current carrying wire? And I say he's making the B field. And then here's my little charge. He's over here. Let's say he's going this way as well. Okay? So, right, the creator of the B field is the current. So now, first I'm going to have to do the right-hand rule for B field created by current. So I'm going to stick my thumb in the direction of current, and then I'm going to flip over to this side of the current, and you're going to see that my fingers are pointing into the page for the B field created by that current. Okay? So my fingers are going to go into the page, so my B field is going into the page created by that current. And then I want to see, well, what force is exerted on that charge due to that B field into the page. So V is up, B is up, B is in the page, and my middle finger is pointing towards the current. So the force will be to the left. So it's kind of a two-stage. Again, yeah. So first, right, the current is making the magnetic field. So I need to figure out what that is. So I'm going to put my thumb in current, and then I'm going to make sure I'm looking at the right side of my thumb, and you can see my fingers are going into the page. So B is into the page. And then I'm going to examine the force acting on that particle with velocity, positive particle with velocity up. So thumb is up, pointer in the page, middle towards current. Now if we're going to do the sweeping version, V is up here. You see I have to rotate my hand until I'm able to fold it into V. To sweep out that plane created by V and V, and then you can see my thumb is pointing to the left if you want to do the sweeping version. Oh, yes.
The first part is confusing. So we don't take it around.
No, you want to stop your fingers at the location that you care about finding the B field.
And why we want to stop it?
We want to stop it because we want to know what B field that positive charge is experiencing, so that we know what force it is acting on, what direction of the force. So I'm going to stop for the B field. I'm going to stop when my fingers are on the right side of the thumb. So I'm going to stop it right there. And you can see that they're pointing into the page. If I sweep it all the way around, then I'm on the left side of the current. So, which you might need if there was a particle over there. And I'm going to skip the magnitudes of those forces, of those magnetic fields, right? We're just going to focus on direction. That's the hard part. So this can be extended to two current carrying wires. Let's say we have I going up here and then I going down here. We're going to do the same thing. This guy's going to create a B field. We already know that over here on this side, that B field points into the page. And then we're going to do the right-hand rule for that current. right, that current's gonna feel force. So you do instead of your thumb in the direction of V, your thumb is in the direction of I. And you're gonna sweep it into B. My brain has, I'll do the 3-finger method, right? I is pointing down, B is into the page, so I'm gonna rotate my hand. And you can see that my middle finger is pointing to the right. So opposite direction currents are feeling repulsive forces. And you can do the same thing with the other side by calculating the B field created by the right current. So let's talk about flux real quick. And a lot of sighs. It's like, is this class over yet? Is this entire physics experience over yet? Not yet. Monday. I'm ready too. I'm kidding. I enjoyed having you guys. It was fun. It was fun. So magnetic flux it's like a mathematical calculation. It's technically a dot product between two vectors. We can express a dot product between two vectors as magnitude vector 1, magnitude vector 2, cosine of the angle in between. The picture of this, right, if this is our surface area, the area vector, right, is defined as a vector that is perpendicular to the plane of the area. So that's our area vector. And then our B field is, at some other angle. And then the angle between them is theta. So this is a calculation or a measure of how much B field is going through an area. And what we know is that if that B field and area combo change at all, we produce a voltage, right? Kind of out of thin air. It's like magic, right? I wave up my magic magnetic wand and I get a voltage, which is basically how we power everything that we have right now. Everything, the electricity that we all generate is because all we're doing is changing the magnetic flux through some area. So we use magnetic flux to calculate the EMF, which is a voltage. Okay. The only time we get a voltage is if the flux changes with time at all, right? And the ways that we can change the flux with time is B could change with time, the area could change with time, and the angle could change with time. Right? Those are the three ways that we can create a voltage from a changing magnetic flux. So let's talk about, the last thing we'll talk about is the right-hand rule for the direction of the induced current, right? Because if you have a V created, if you have a voltage, then you're going to have a current, right? Voltages produce energy, give particles energy to move. And moving charges are currents. So let's do the final thing we'll do is a right-hand rule. So let's say that here's our area. Let's say we have a B field and B is increasing. Okay, what direction is the induced current going to be? Well, the first thing we want to do is determine the B field direction, which I wrote down. Okay, I can't spell it all because I'm like rushing. Determine B. 2 is flux increasing or decreasing. 3, find your B induced, which opposes the flux change. It doesn't oppose the field. It opposes the change, right? It doesn't oppose B. It opposes the fact that B is increasing. So if B is a vector pointing up and that B vector is getting bigger and bigger, how do we shrink it? We add a field in the opposite direction. So our B induced is going to point down. And then, looking from above, our fingers are moving in a clockwise fashion. So B induced is down. And then we do our right-hand rule on B induced. And we see that we get a current, an induced current. that flows clockwise. Oh, did I draw clockwise? No, I did not. No, I did not. There it is. So, this can get really tricky because, and I have this step by step, this is all written in these steps are written in the sheet. So, the tricky part is I may or may not give you a friendly B field vector. I may make you find B using a current or using a bar magnet, right? So let's talk about if B is created by a bar magnet. We didn't review that. So B fields point out of north poles and go into south poles, okay, on the outside. And then remember we had this discussion, on the inside, they go from south to north, right? Inside the object, they go from south to north, but outside the magnet, which is what we care about, it flows from north to south, okay? So now if I have my loop again, and instead I am dropping a bar magnet instead of a B field vector, let's say north is down, well, I'm going to use that bar magnet to determine what the B field direction is. And so since it points out of north, I'm going to get my little arrows, right? So my B is pointing out of north. And then now the increase or decrease in flux has to do with the motion of the magnet, right? So if the magnet is moving down with velocity v, well, then the flux is increasing, right? Because that strong magnet, the strong part of the magnet, right? The closer you are to the north pole or the south pole, the stronger the magnetic field is. We're bringing that strong field towards the loop. So the loop is feeling more and more B, right? So B is increasing. And therefore the flux is increasing. If instead we're pulling the loop away, or not the loop, but we're pulling the magnet away, then the flux is decreasing. And so then why do we care about the flux increasing or decreasing? Because that's how we decide how to do the right-hand rule, right? So whenever flux is increasing, B induced points opposite to the existing B field, the blue one. And if the flux is decreasing, then B induced will point in the same direction as B. As blue B. So that's the general idea. So I could also use a current carrying wire as the source of the B field, okay? You have lots of practice questions to look at. And so then after that is basically electromagnetic waves, polarization, AC circuits. The AC circuits, let me just briefly talk about that. I'm going to skip polarization and electromagnetic waves. It's in there, but I think I might have done two. Two for magnetic flux and magnetic induction. It's kind of combined. There's two questions. One conceptual, one calculation. There might be three. Two. Let's put 2 or 3, because I like it. So you get more of it. Yeah. So let me real quick talk about the section that we have. You have not been tested on. I don't know why I'm writing the number 10. AC circuits, and I'll just want to briefly prep you on what. So understanding the difference between voltage, the RMS voltage, and the voltage max or amplitude, okay? Those mean the same thing. So what is that? So AC voltage means you have a voltage that's varying in time, and it varies in time according to a cosine function. Pretend that that's an evenly spaced cosine function. If this is your voltage versus time, this guy right here is the amplitude, right? This is V amplitude, also known as the maximum V. The RMS value is this value right here, which you can get by taking that amplitude or max, they mean the same thing, and dividing by the square root of 2. Okay, and that same goes for current. Same relationship. Okay, max current or amplitude of the current is equal to the, no, amplitude, no, IRMS, right? The current, RMS current is equal to the amplitude divided by square root of 2. Everything is moving very quickly. Transformers are the other, so you're gonna have one question about this and one question about applying transformers. It's a very straightforward plug and chug, okay? So don't worry too much about that. And that's the end of it. And there's some general tips. So my suggestion to you at this point is to be giving yourself mock exams. Okay, that's what all I would be doing at this point, is giving yourself timed exams. Don't make it 2 hours. You don't want to do like a 30-minute exam of 5 questions and pick random ones, not from the same